this section and the following two sections will cover triple integrals. As for double integrals, the triple integral is defined as the limit of Riemann sums. Let's begin with a function of three variables defined on a rectangular box as shown in this figure. W is f of x, y, z, and the point x, y, z is in the box. In the x direction, a to b. In the y direction, c to d. In the z direction, r to s. To define a triple integral, we first divide the box into sub-boxes. For some positive integers, lmn, we define delta x, delta y, delta z, so that in x direction, L subintervals, y direction n subintervals, and z direction n subintervals. Each of these subbox is called with bijk. So the bijk is the ijkth subbox, and it can be expressed in this way. Of course, the volume of the subbox will be here delta V, which is delta X, delta Y, delta Z multiplication. Here the triple integral of f over the box B is defined in this way. Triple integral over B and f over x, y, z dv. Now this is volume element. Here this is Riemann sum. And for the volume and for the function, we try to get a typical value at x star ijk, which is in bijk, and that is playing the role of height, and that is the volume. The product is summed over all sub-boxes, and we try to get more partitions in every direction, and the limit is the triple integral. That's the definition of the triple integral. And that's not really new. When we try to define double integrals, we did the similar way. Now, for the triple integral, we may consider Fubini's theorem. If f is continuous on the box, then the triple integral can be obtained with this iterated integral. So it is z innermost and y integration and x integration. Of course, you can get the same answer by using other the choices of order. There are 6 choices and 3 elements, so there is 30 factorial is 6. So there are 6 different ordering, but everyone will get the same answer. And that is Fubini theorem over the rectangular box. So main idea is in the iterated integral. You can do it step by step, and z direction and y direction and x direction. Okay, let's try to solve this problem. Evaluate the triple integral over b x, y, z squared dv, where b is this box. Okay. And by using the Fubini theorem, the given integral can be written. Okay, let's try to use a blue pen. that will be in x direction. Any direction will be fine. Okay, x direction first, then is from 0 to 1, and y direction next, minus 1 to 2. And z direction is from 0 to 3. And then the integrand is xy z squared. And that's dz, dy, and dx. Now, this one, the integrand is separable so that we can integrate the separately along with the x component, along with the y component, and the z components. Exactly the same as for double integrals. Okay, from 0 to 1, x dx times integral minus 1 to 2, this is y direction, so y dy times integral from 0 to 3 z squared and dz, right? Okay. From the first one, we'll have 1/2. From second on, okay, there's half y squared from minus 1 to 2. And the final one is 1/3 of z squared, z cubed, okay, cubed, and from 0 to 3. Okay, the first one is a half. And this one, once y is 2, then 4, y is minus 1, then there will be 1. 4 minus 1 is 3, so that's 3 over 2. And the final one is now the 27, so it's a 9. So we have a 27 over 4. That's the final answer, right? Triple integral can be applied for general boundary region E. In this case, a good strategy to get the triple integral is here. First of all, you have to recognize the domain. So try to visualize it in your brain or on the paper. And then separate the domain into two portions. One is two-dimensional region, and the other one is the vertical direction and the one-dimensional vertical direction of D. So along with this separation, you can get integral much easy way. The triple integral is changed into now outer double integral over D and inner one in one-dimensional integration. Here the principle is that you must find a good scheme to cover the whole domain without missing, without duplicating. Let's go on a journey for triple integrals. Evaluate the triple integral over E, where, okay, and then the integrand is Z, a simple one, where E is the solid tetrahedron bounded by 4 planes, x equals 0, y equals 0, z equals 0, and x plus y plus z is 1. Let's try to visualize the solid tetrahedron. Okay, we have a 3D coordinate, x direction, y direction. That is z direction. X is 0 as y's plane, and y equals 0 as x's plane, this left side. Z is 0 is bottom plane. So they are just coordinate planes, and x, y, z summation is 1. That is, now once y is equals 0, then x is 1. So intercept in x-axis is 1. The same way, the intercept in y direction is 1, again 1. So that the plane, last one is passing this 3 point, this is 1, That's 1, that is 1. So that we can draw the tetrahedron connecting this 3 point. Okay, so now we can see the tetrahedron. We have to express this tetrahedron and by saying 2 parts. One is D, of course, here there must be D on the bottom plane. The surface must be D. And for each xy on D here, the E is making from bottom to the slanted surface. So this is a bottom, Z is 0, and top Z is on this slanted surface coming from this one. So that is the same as Z is 1 minus X minus Y. That means that E can be D times from 0, Z is from 0 to the top Z is 1 minus X minus Y, right? Okay. So the given integral must be double integral over D, and now Z direction bottom to top of Z, right? And then integrand is Z, and we have the vertical direction integration, and now the horizontal direction integration over there, right? So first we try to evaluate that inside. Okay, double integral over there, and that is half Z squared, and then Z is from 0 to 1 minus X minus Y, right? Okay, dA, we can get it easily, double integral over there, and that is half is here, and that squared, so that 1 minus X minus Y squared, and dA. Now, we have to evaluate this double integral. Let's try to visualize the more, we can use it more conveniently. Okay, so here, from that bottom, we can see easily, okay, if this is X direction, if this is Y direction, it's touching, the intercept is 1, again 1. So here 1 and 1, like that. Yeah, this is 1 and 1. Okay, this is 1 and 1. And this is exactly D. We can access the domain for each X between 0 and 1 vertically from 0 to top Y. Okay, that is X plus Y equals 1. When Z equals 0 is the bottom, on the bottom Z equals 0, so this line must be X plus Y equals 1, right? Okay, so we have to access this region. In X direction is from 0 to 1. Okay, so that we'll put here dx, and Y direction for each X, so bottom must be 0, and top Y must be 1 minus X. This one is the same as here, Y equal 1 minus X, right? Okay, and we have half 1 minus X minus Y squared and dy. Okay, now let's try to get this one. Okay, that is, okay, half will go out. It's okay, we'll put half outside from 0 to 1. Now for that portion, let's try to get its antiderivative. Okay, that is some coefficient, and then major part will be 1 minus X minus Y cubed, right? And we'll evaluate from 0 to 1 minus x. Of course, here, this is y values, right? Y is 0 to 1 minus x. And after getting this one, we try to get x integration. Now, we have to decide this unknown. In order to do that, we differentiate this portion. And 3 and 1 minus x minus y squared. And we try to make y derivatives here, the coefficients minus 1. Compared with this integrand, here we have minus 3 extra component. So that we put here 1 over minus 3, right? Okay, now we'll put out 1 over 3, so that 1 over 6, and from 0 to 1. Now, along with this minus, first y equals 0, then there is 1 minus x cubed, and y is 1 minus x, and then it is 0. So we have that one. Okay. So from this one, we can get the final answer. Now, for that one, that is 1 over 6, and this is from 0 to 1, and then, okay, let's try to get the antiderivative. So 1 minus x to the 4, and if we try to put here, okay, minus 1 over 4, the coefficient, then after differentiation, okay, this will be cancelled. Okay, so it's 1 minus x to the 4 minus 1 over 4. And we are trying to get evaluation from 0 to 1. So it is 1 over 6, and that is 1 over 4. So we have 1 over 24, the final answer. Okay? Okay. Now let's try to solve this problem. Evaluate the triple integral over e square root of x squared plus y squared dv, where e is the region bounded by the paraboloid, this paraboloid and the plane. The paraboloid is upward, and at z equal 4 is cut by this plane. So let's try to visualize it. We have z direction, and then this is y direction. This is now x direction. Okay. Now look at this y and z. The paraboloid is made in this way. It's cut by the plane z equal 4. So that is 4, like that. So E is this whole thing. Now the strategy is we have to separate this E into two parts, so that we have to get two-dimensional area. In order to do that, let's try to project this onto the plane, flat plane. Then we have that one. Let's see, that is D. Then for each point in D, and the bottom is this the paraboloid, and top will be 4. In Z direction, bottom to top. Bottom Z is coming from this paraboloid, so that there's x squared plus y squared, and top is always 4 because it's cut by the flat plane. So E can be expressed with these two portions, D times that one in Z direction. Right? Okay. But what is D now? And that one, the circle, is the same as this disk along with that circle. When it is 4 and z equal 4, there's x squared plus y squared is 4, so that this circle is x squared plus y squared equal 4. So it's reduced to a disk, right? Now, the given integral is two-dimensional integration, out integral. Inner integral is bottom, z is x squared plus y squared. Top z is 4, and the integrand is x squared plus y squared. And square root of that. And there is z direction, and now and over d. Okay. Now this is z independent, so we can get it quite easily. Integral over d, and this is a sort of a constant. And this is interval length, so that here we have 4 minus x squared plus y squared. Okay, this whole thing is the integrand for this integral. Okay, to get the integral, we have to do this computation. Now, D is a polar region. Now, if disk of reduced to is a whole circulation from 0 to 2 pi, and R is from 0 to 2, because it's reduced to. This must be R, and this portion must be 4 minus R squared. And when we get polar coordinates, and we have to, we should not forget the scaling factor R and dr d theta. Okay. Now, this integrand is theta independent, so the theta integration is 2 pi. And then this one is from 0 to 2, r squared, so the 4r squared minus r to the 4 dr, so that is 2 pi. And here this is 4 over 3 and r cubed minus 1 over 5 r to the 5, and then r is from 0 to 2. Right? Okay. Now, so that this m is 2 pi, and then here is 32 over 3 minus, okay, that is again 32 over 5. So 32 can go out, so it's a 64 pi, and 1/3 minus 1/5, which is same as 2 over 15. So that eventually we have 128 pi over 15, right? Okay. When we deal with double integrals, once the integrand is 1, then, okay, integral over d and 1 dA, then they're the same as the area of the we did for as an application of double integrals. Here, as an application of triple integrals, we consider the integrand is 1, and then the triple integral of the function 1 over the region E is the volume of E. Is quite simple expansion from this double integral case, right? Okay, now let's try to solve this problem. Use the triple integral to find the volume of the tetrahedron T bounded by 4 planes, and x equals 0, y equals x, and z is 0, and this plane. So let's first try to understand the tetrahedron. So visualize it, x and y direction, and z direction. Okay, x0 as yz plane, this back plane, and y equal x, the plane is a plane here along with y equal x. That line is now y equal x. In fact, it is plane in whole z direction, and it is made in this way. There's plane. Now z equals 0 as bottom plane, and x plus y plus z equal 2 is plane passing the intercept here 2, and again there is 2, and again z direction 2. So that, okay, now this one is a line, and that one. Now if you connect to this one, then it's whole tetrahedron. But rather than that, in fact, we have to get that side. Only bottom is only this side, because here, rather than this, in the side plane, the problem is saying y equal x, which is that plane, so that side. And we connect one more to see the tetrahedron from here to there. Can you see the tetrahedron? This is bottom, and one side, another side, and back side, right? Okay, we want to find the volume of a tetrahedron by using the triple integral. Right? So now we have to, okay, this T tetrahedron, that must be D times, okay, something like that. We'll try to get it. Okay, here D is of course that one, and for each point over there, the bottom Z is 0, and top Z will be on the plane, but the plane is given in this way, so that bottom Z is 0, top Z is from here Z equal 2 minus x minus y. Okay, not so much complicated. 2 minus x minus y. So the volume of the tetrahedron is double integral over D, and now the final direction from 0 to 2 minus x minus y. Now the integrand must be 1, and dz and dA. Right? Okay, double integral over D. We try to finish this one. It's 1, and so that the integral must be the length, that is same as 2 minus x minus y, and dA. Now, to finish the calculation, we have to access D. Okay, now let's try to visualize D. It's on xy plane. So here we try to make xy plane. There's x direction, there's y direction, and this line is passing here 2 and 2. So there is 2. And this one is along with here x equal y, that is x equals y, and this region is near around the y-axis, so that one. Okay, that is D. Right? Of course, you can get this one quite easily. That is 1. So you can access this region D. First, x is from 0 to 1, and y is from, okay, for each x, this is bottom y, there's top y. Bottom y is x, and top y is that one. The equation of that one is this one. That is same as x plus y equal 2, x plus y equal 2, right? So the bottom y is x, top y is 2 minus x. Okay, so the integral is from 0 to 1 in x direction. In y direction, bottom y is here, that one. here to there, right? From here to there, bottom y is x, top y is from here, and 2 minus x. And the integrand is 2 minus x minus y and dy. Yeah, we get it. Now, okay, from here, from 0 to 1, in y direction, let's try to finish this one. That antiderivative must be, okay, I write down this one, minus half 1 minus x minus y and squared. And we have here y must be from x to 2 minus x, right? If you try to differentiate, then you'll get that one. So it's antiderivative. So let's try to evaluate them. So 1/2 can go out, and from 0 to 1. Now, along with negation, we try to get it here. Okay, there's not 1. There must be 2. And this one must be, okay, once y collects, then must be 2 minus 2x squared. And then once y equal 2 minus x, okay, then this is 0. So we have this integrand, and we have to get integration. Now there's 4 can come out, and then, okay, let's write down in this way, from 0 to 1, and 1 minus x squared dx. Then, and that will be 1/3. The integration must be 1/3, so that 2/3. That's the final answer. You can get it quite easily. That is 1/3. Okay. Okay. Now, when you are dealing with triple integral, sometimes you have to change the order of integration. Here we'll consider how to change order of integral. Okay. Now, in this example, and innermost one is x integration, next one is z integration, and outmost integration is along the y direction. Now we can change the order when, for example, if we try to consider x and z, then that means we are considering only this portion. And this one is defined. In any case, it's a function of y, and then here for each y, it is okay. So we are using the exactly same technique for double integral to change the order x and z. We can do it. Or we may consider z and y change order. Then, okay, let's try to consider from here to there. Then this is after integration. This portion is after integration, x integration, it will become a function of y and z. So let's say this is g of xy. So we can, once we fix this one, then we can change order between z and y, because it is a function anyway, function of xy. In fact, that is after x integration. Okay, I'm sorry. This is function of y and z. Okay, this is function of y and z. So that just we fix it, then we can change the order of integration. So either way, we can do it. First, we'll try to do x and z change. Okay. So the first one, we try to change order between x and z. That means that here we are focusing on only this inner integral. Okay. Now this is x and z direction. So y must be between 0 and 1. Some number, some y between 0 and 1 is given. So that, however, in this integration is constant, so that you can change the order quite easily. But let's try to visualize. Once it is a rectangle, then from Fubini theorem, we can change the order quite easily, right? Y is some number between 0 and 1, because dy, y is from 0 to 1, so that for a fixed y is between 0 and 1. Okay. Now there's x and z direction. Let's try to visualize the region. There's x and z. Okay. Now outer integral is z direction, so that from y to 1, sum y to 1, right? Y to 1. And for each z, x is moving from 0 to y. X is moving from 0 to y, so that the same distance, like this, that will be y. So in fact, this one is a square. But for z moving from here to there, and x is moving from 0 to y, so that the region considered as this one, rectangle. So for rectangular region, we can exchange quite easily. And also we can see easily here y independent. In fact, yeah, that one, and x and z, so in kind of constant. Okay, so the given integral can be written from 0 to 1, the same, outer integral must be the same, and inner integrals can be here changed, 0 and y, and here from y to 1. Okay. And that is f is here, and dz, and dx, and dy. Okay? So we get new order here. Okay, let's go to another one. This time, we try to change z and y. Now, in this case, we consider this part as a function of y and z, so that it's a function, and we can change z and y by using exactly the same technique we explored for double integrals, right? Okay, let's try to visualize the region, and okay, we'll try to make a picture here. Y and z. That is y direction. That is z direction. Okay. Now, out integral, y is moving from 0 to 1. So it's 1. Now, in z direction, bottom z is y. Bottom z is y. So that is z equal y. And top z is 1. So that, like that. So here, for each y, bottom z and top z, we are accessing this region vertically like that. So that is the region. Right? So from this one, here, innermost one is fixed as a function, and then the given integral can be written in this way. Okay, now we have to access this one horizontally. Z is moving from 0 to 1. 0 to 1. For each z, now y is moving from here, bottom 0. Okay, that is a bottom is 0. And then y is moving to z. Okay, this y is same as y equals z, so that bottom y, top y. So that is C. And innermost one is the same. Okay, that is the encircled one is the same. Okay, this one, this portion. And this is now dy and dz. Okay? Okay, this portion must be here. So in this way, you can change the order. Of course, here that is dx. The inside we have dx. So we have xzy, this one order, and zxy, and xyz. And after doing this one, for example, if you try to now change these two again, then we'll have here yxz. In this way, by changing adjacent variable, the order, you can get new order of integration. So you can get eventually all 6 of them. This is how you change the order of integration. Okay, just here's the hint is change the order for adjacent 2 variables in the integral, keeping the other the same. So that now we try to only change the order for that one, 2, and again, and these 2, z and y. And after that, and you can make again, change again, then you can get all of them. Okay? Don't try to change, for example, x and y. You'll make easily a mistake. So don't do that. So only play with the 2 adjacent variables and integral, so that that is logically okay, because now I'll explain again. And once we try to change the z and y, then inside this portion after integration is a function of y and z, so that the function is staying there without changing. So only we are trying to change the integral for double integral. Right? But you did this one when we learn double integrals. Okay? Okay, that's the end of the section. Thank you.